D is a finite characteristic, but in fact, characteristic of D, if I write it shortly using this notation, is less than or equal to this. Okay. Now, think of this situation here in exercise 6 with n in place of n, and in place of a we have ma. You see, we already had in the solution to exercise 6 that ma is not equal to 0. So that satisfies this condition. Why is n non-zero? Because n is greater than 1. So it is non-zero. And their product is 0. Okay, so this particular situation satisfies the hypothesis of exercise 8. So D must be of finite characteristic. That we already know because we started with that. But this extra information, that characteristic of D has to be less than or equal to absolute value of this n. That means characteristic of D should be less than or equal to absolute value of this n. Now for us this n is positive, so absolute value is equal to n. And what is characteristic of D? Characteristic of D is P. So that means I have concluded from all these considerations that P is less than or equal to n. But this is a direct contradiction to this, that P is greater than n. So that's how the solution to exercise 8 is contradicted. Okay, and this completes the solution to exercise 6. That's how all the things can be justified. Okay. Now we see, after this complicated relationship between these two exercises, now we go to exercise 9. If R is a system satisfying all the conditions of a ring, of a ring with unit element, okay, that thing is also there. With unit element, with the possible exception of A plus B is equal to B plus A. Prove that this axiom must hold in R, and R is thus a ring, and a hint is also given to us, and that actually solves the exercise for us. Expand A plus B times 1 plus 1 in two ways. Two ways means two different ways. Okay, so what is this exercise saying? It is saying that we have a system although Einstein does not mention addition multiplication explicitly, but those things are there. We have a system where we have an addition and a multiplication which satisfies all the conditions of a ring with unit element except possibly commutativity of addition. We don't know whether this is true in R or not. R satisfies everything that is satisfied by a ring with unit element, all the axioms. Okay, note that we are not saying anything about commutativity of R. Whether multiplication is commutative or not, that is not our concern here. But we don't know whether addition is commutative. As such, we can't say that R is a ring. But if these conditions are satisfied, then we have to prove that this condition of which we are doubtful, that also must be true, and hence R is a ring. And the hint is of course this. So let's see the solution. Having the hint, this is now almost trivial. We have a plus b times 1 plus 1 equal to, if we start by using the left distributive law, then this will be equal to a plus b times 1 plus a plus b times 1. But keep in mind that we are not in a ring now. We have to prove that the system is a ring. So while applying these axioms, we have to be careful not to use this ever, because then we won't prove anything. Here we are using left distributive law, which is available to us, because except for this one, everything else is available, excluding of course commutativity of multiplication. Similarly, this becomes a plus b plus a plus b. Okay, using the fact that 1 is the unit element. That axiom is also there. And again, this is equal to, now we use the right distributive law, which is also available to us. And this becomes equal to, okay, now unlike the previous case, here we have to use the left distributive law again. Doing that, we get a1 plus a1 plus b1 plus b1, which gives us a plus b plus b. Okay. Now these two things are actually equal because we have started from the same expression. Hence, a plus b plus a plus b is equal to a plus b plus b. Note that in writing this we have not used any brackets. That's because addition is associative, that thing is there. So without being ambiguous, we can write an expression like this. It does not matter in which way we bracket this expression, using how many brackets we want, but we will ultimately get the same thing. Now, using the left and right cancellation, laws in the group R plus, we have B plus A equal to A plus B. Note that in spite of possibly not having this condition, this is still a group. The only thing is that we now don't know whether it is abelian or not. We are trying to prove that it is abelian. However, being a group, the cancellation laws are available to us. So using the left cancellation law, we can cancel this A from both sides. Using the right cancellation law, we can cancel this B. So we are left with B plus A equal to A plus B. And that's what we have to show. Thus, addition is commutative and R is thus a ring, and that ends the solution. Then we move to the 10th one. It's somewhat easier than the others. Show that the commutative ring D is an integral domain, or we have to include that extra condition also. We have to carefully include that. Is an integral domain if and only if for A, B and C in D with A not equal to 0, the relation SC is equal to, or AB is equal to SC implies B is equal to C. So this is an equivalent condition for a commutative ring to be an integral domain, a commutative non-zero ring. Okay, we have lost a portion of the bisecting line. Solution. So first assume D is an integral domain. Let A, B and C be any three elements in D such that A is not equal to 0 and AB is equal to SC. Then A times B minus C, this is equal to AB plus A times minus C, which is nothing but AB minus AC. This is equal to 0 because AB is equal to AC. So we are in an integral domain and the product of two elements A and B minus C is 0, out of which A is non-zero. So to not have zero divisors, B minus C has to be 0. Since D is an integral domain and A is not equal to 0, A times B minus C equal to 0 implies B minus C is equal to 0 or B is equal to C. So we have proved this part, assuming that D is an integral domain. Conversely, assume that D not equal to 0 is a commutative ring such that for elements A, B and C in D with A not equal to 0, AB equal to AC implies B is equal to C. We have to prove that D is an integral domain. It is already given that D is non-zero and commutative, so it's enough to show that D has no zero divisor. Okay, so let alpha and beta be two elements in T such that alpha is not equal to 0 and alpha beta is equal to 0. Then alpha beta is equal to 0, and now 0 can be written as alpha 0 by elementary ring property. So our hypothesis implies, what is the hypothesis? This is the hypothesis. If we have three elements such that AB is equal to AC and A is non-zero, then B has to be equal to C. Now also we have three elements, alpha, beta and 0, such that alpha beta is equal to alpha 0 and alpha is non-zero. So beta must be equal to 0. Thus D has no zero divisors and so D is an integral domain. Then exercise 11. Prove that lemma 3 to 2 is false if we drop the assumption that integral domain is finite. It is that result which says that every finite integral domain is a field. Now if from this we drop the hypothesis that the integral domain has to be finite, then it's not necessarily a field. We have to prove that, of course, by some example. Note that, so what is it that we have to do here? We have to produce here an example of an integral domain that is not finite and that is not a field. Okay, if it is finite, it has to be a field. That's what lemma 322 says, states. But if it is not finite, then things can go wrong. Note that the ring of integers, we need not go far. The very first example is an integral domain which is infinite and it's not a field. Is an integral domain that is infinite and it's not a field. Why it's not a field? That you already know, because the only non-zero elements in it which have multiplicative inverses are -1 and 1, and their inverses are also respectively -1 and 1. Everything else, all other non-zero integers, none of them has multiplicative inverse in the ring. That's why it is not a field. Okay. Exercise. Let's do one more. After exercise 13, we have two more exercises in this state, 14 and 15, which we will do later. Later means we will do, but in another video. Prove that, okay, this is rather easy. Prove that any field is an integral domain. Let's recall the definition of a field. Okay, let F be a field since the non-zero, or I can write it briefly like this, since f minus 0, this subset of f is a group, or not just any group, is an abelian group under multiplication. That's the definition of a field, right? The non-zero elements in a ring, if they form an abelian group under multiplication, then the ring is called a field. Since this is an abelian group under multiplication, this is not empty set. Since this is a group, it has to have at least one element. So that's why this is not empty set. Hence, the field is not the zero ring. So that's how no field is the zero ring. In a field, since there is a unit element also, 1 is always not equal to 0 in a field. In a general ring, that's not necessary. Okay. Hence, f is not equal to 0. So that means our ring is non-zero. F is also commutative, right? So we can, if we want, we can use the result of exercise 10 to prove that f is an integral domain. What do we need? We need 3 elements in f, one of which is non-zero, and this relation should imply this: ab is equal to ac implies b is equal to c. So let a, b and c be 3 elements in f such that a is non-zero and ab is equal to ac. We have to prove that b is equal to c. If we can do that, then f will be an integral domain by exercise 10. Then we can write b like this: 1b, and 1 can be, okay, let me continue from the next line. 1 can be written as A inverse A B. Why? Because we are in a field, so every non-zero element has a multiplicative inverse such that this product is the unit element. By associativity of multiplication, this is equal to A inverse AB. Now AB is equal to AC according to our assumption. Again you use associativity. This is equal to 1C, this is equal to C. So that's how we get B is equal to C. Hence, by exercise 10, F is an integral domain. Okay. Later at some point we will see that every integral domain is sitting inside some field, namely its field of fractions. Just like the integral domain of integers is sitting inside the field of rational numbers. In that sense, every integral domain can be made to be inside, in some sense, a field, a larger field. Okay, so after this we have the other 2 exercises which are not really about ring theory but about some applications of the pigeonhole principle. So we will see that in another video, in the next video.